Please welcome computer scientist at Los Alamos National Laboratory, Scott Paikin.
Welcome to the invited talk session on quantum computing. We have two speakers in this session who will each provide their insights into the intersection of quantum computing and supercomputing. Our first speaker is Alba Cervera-Lierta from the Barcelona Supercomputing Center. Dr. Cervera-Lierta works on near-term quantum algorithms and their applications and artificial intelligence strategies in quantum physics. Since October 2021, she has served as the coordinator of the Quantum Spain project, an initiative to promote and finance a competitive and complete quantum computing infrastructure in Spain. Please welcome Alba Cervera-Lierta.
Okay, thank you very much, and thanks to the organizers for inviting me to give this talk and to share what is the research that we do at the Barcelona Supercomputing Center regarding the quantum and HPC integration. So let me show you the outlook of my talk. First of all, the first take-home message that I would like to be very clear of is that supercomputers do not compete with quantum computers. They will become one of their partitions, and the reason is because we are talking about a specific purpose devices that have a lot of capabilities, that have a lot of potential, but they are not replacing what supercomputers are doing. Maybe they are replacing it for particular applications where we know that supercomputers are hard to manage, for instance, the simulation of quantum physics, but not in general all possible applications. So therefore, what we envision is that a user or that has a particular application, an algorithm, will need an hybrid task manager that distributes the algorithm into the different partitions that they need. That could be the general purpose partitions, accelerator partitions, and also quantum computing partitions, or even more if we develop other technologies. Therefore, installing these kind of devices in supercomputing centers seems like the natural way to continue, together with the efforts, of course, that vendors that are developing these machines are also doing. And in the end, this will become another partition to be used by all of us. So why a supercomputing center may be interested in quantum computers in the first place? So I think there are at least three main reasons. The first one is because this is a new model of computation. So we like these new models of computation. We want to explore what are the capabilities that they have. And also because we know that we are reaching the limit of traditional computation. So the natural way that we can extend the capabilities of our high-performance computing devices is precisely towards the specialization of the computing chips. So quantum computer is just another type of way to do that. And that's why we want to increase the capabilities of our supercomputers by having different ways to perform computation and to explore this computation. Another reason is because we want to satisfy the user demands. So if users want to explore this computational paradigm, then we want to make the effort to install these devices in our center and make sure that they have this access provided by, in our case, by a public institution. So this is one of our main missions of a supercomputing center, and that also means that we have to make an effort to adapt our infrastructure to welcoming this technology that is so different to the standard traditional computers. And finally, because supercomputers have applications in quantum computing and the other way around, and that's the rest of my talk, I will develop this further. But basically, there are many applications that require both supercomputation and also quantum computation. So this mixture between these two paradigms will encourage the development of certain applications, and we believe that could open the path to develop new science. Okay, so let's dive into it. And for those that are not familiar with quantum computing, let me explain very briefly, high level, how a quantum computer works or what is the structure of a quantum algorithm. First of all, a quantum computer requires classical computation. By classical, I mean anything that is not quantum. So we use this word classical in comparison with quantum because it's classical physics what describes traditional computers. So this classical computation appears in the software part of our algorithm. So we program a quantum computer from our laptop. We use standard libraries like NumPy libraries written in Python code, most of them, but also in Julia, in C++, in JavaScript. There are different ways to do that, depending on who is developing the hardware. So this software will help us to create a set of instructions that will be sent to the control electronics that generates the necessary physical interactions to the hardware, okay? This hardware is the purely quantum part, is where the quantum processing unit is located, where the qubits are the physical objects that generate these qubits, these basic units of quantum information are located. And then this hardware returns a signal. And this signal is our result of the computation, but it needs to be post-processed. So basically, the workflow that a quantum algorithm will follow is there needs a pre-processing part. We need to generate these quantum circuits. We need to generate the quantum algorithm. And to do that, we may require the use of other libraries or the use of other applications. Then, once we have this set of instructions, we send them to the control electronics. It's executed in the QPU. And then the result needs to be post-processed. And in many cases, this is a loop. So we need to repeat this loop over and over. On top of that, quantum computing is a probabilistic model of computation. So we need to execute the exact same circuit multiple times in order to obtain a probability distribution, and that will be the result of our quantum computation. So as you can see, most of the parts are run in a traditional computer, are run outside of the quantum computer. And that's one of the main reasons why we are not replacing a traditional computation, because we still need them. There are different types of quantum algorithms, but let me classify them in these three big categories. The first one is quantum simulation algorithms. This is one of the main reasons why we are building these quantum computers, because we know that simulating quantum physics is exponentially hard with traditional computation. Of course, we can run several approximations. It depends on the quantum system that we want to simulate. But in general, to obtain a very precision simulation, we will need an exponential amount of resources in terms of memory or time. So that's why that was the main motivation in the 80s of why we wanted to construct a machine that follows the same laws of quantum mechanics the things that we wanted to simulate. So these quantum simulation applications have many applications in chemistry, material science, in nuclear physics, etc. Basically understanding how the world works, in particular how the quantum physics world works. Then we have the quantum advantageous algorithms. These are those that are better than the classical version. So we know that there is an exponential or polynomial computational advantage. And this was something that was discovered later, that we can use the specific properties of quantum systems like superposition, entanglement, interference, in order to exploit the mathematical symmetries or certain problems and reduce the number of operations, even exponentially, in the case, for instance, of integer factorization. So this has a lot of applications, in particular integer factorization in cybersecurity. But there are other applications that we are also exploiting, and also they could be quantum advantages. And finally, we have the heuristic algorithms. So those algorithms that require a strong classical subroutine, so traditional computing subroutine, in order to optimize a certain parameters of our quantum circuit. They are also known as hybrid or variational quantum algorithms. And I call them heuristic because we don't have the same performance guarantees as the quantum advantageous algorithms. But they are a very good trial field to explore new physics and to explore this model of computation, because this kind of algorithms can be run on current-term hardware. So it's something that we can run now. So how HPC can enter into quantum computing realm? There are different ways, so let me show you some examples. Of course, I will not like to constrain to these particular examples because there are many more that they can appear. And I believe that since we are installing these devices in our centers, more applications will emerge now that the HPC community is getting involved. So starting with quantum simulation, we have simulated quantum physics for the last years, of course, using traditional computers, using HPC. And we can do it even further and even better, exploiting certain algorithms that have been used in physics. So first of all, this classical simulation of quantum systems and circuits is exponentially hard, as I mentioned before, unless we make some assumptions. So we know that if the quantum circuit has a particular set of gates, if the precision is not is not very high, or if there is a low entanglement or quantum entanglement in our circuit, then we can do this simulation efficiently using HPC. Another reasons to use a quantum emulator is that we don't have good or big quantum computers yet. Therefore, researchers like me that want to test their algorithms and see how they scale and see what are the capabilities that they have, we need to simulate that with something because we don't have the proper hardware yet. And for that, if we have a proper quantum emulator, we can simulate larger quantum circuits and try to extract the most information from them. Then, as I mentioned, there are many quantum applications that don't require quantum computation because these assumptions that we can make. And on top of that, what is happening also is that we are discovering new ways to perform certain classical algorithms by inspiring ourselves with what happens in quantum computing. So there are some algorithms called quantum inspire that they take inspiration of how the quantum algorithm works and try to translate it to classical computation. So this will not be possible for all possible applications, but this is also a very high importance field in our community. Also, we need methods to verify quantum computers. So eventually, we will not be able to verify the result of a quantum computation because we cannot simulate that with supercomputers once we have millions of qubits, of course. But we can verify some parts, or we can verify the short term. So that's also another application where HPC will play an important role. And finally, the design of quantum devices requires a traditional computation. So how I'm putting together all the capacitors, all the resistances, all the inductances to build my quantum chip. So we need to design that. We need to simulate what will be the capabilities of the chip that we want to construct. So to design quantum devices, we can also use high-performance computing. As I was mentioning, there are several techniques to do this quantum simulation efficient. And one of these techniques is called tensor networks, and it has been used since the 90s by the physics community, in particular in condensed matter physics and many-body physics, and now it's being exploited in HPC. And the reason is because the HPC community is getting aware of this type of applications in physics, and they are taking them and optimizing it further using distributed computation. So we can use an HPC to perform the contraction of all these tensors altogether that will represent our quantum circuit in a distributed manner, and we can simulate very, very large quantum circuits with that. And in particular, at the BSc, we work on quantum emulation, and we have developed different libraries using different distributed workflows to orchestrate all these tensor contractions between the different nodes of Mare Nostrum, and we continue working on that. So this is a natural application that an HPC center can do for quantum computing. Going to the second types of quantum algorithms, these quantum advantageous algorithms, the ones that we know that they have an advantage, a computational advantage. These algorithms, unfortunately for us at current term, they require quantum error correction. So let me step back a little bit. So the state of the art now in quantum computing is called the noisy intermediate scale quantum computing era. Noisy because the qubits that we build and the operations that we do with them have errors, and these errors propagate along the quantum computation. And intermediate scale is because we still need to scale these devices. So of course we have large quantum chips, but we still need millions and millions of them. So current quantum processing units are not fault tolerant. So that's very important because that means that we cannot use these quantum advantageous algorithms in the current term. So the solution to that is called quantum error correction, and that means that we can encode the quantum information of the logical or perfect qubits into a few noisy or physical qubits. And this quantum error correction requires certain cycles that has to be repeated along the computation. So we need to measure some of the qubits. With that measurement, we can infer what was the error that occurred, and then take a decision to apply a quantum gate or a quantum operation to correct that error before the next gate is applied. So this is happening along the quantum computation, and we cannot stop the quantum computation, because if we stop it, we lose the quantum properties of all of it. So these quantum error correction cycles have to be very, very fast, and all of them is happening outside of the quantum computer, outside of the quantum chip. So we need this very fast integration between the quantum chip and some kind of external subroutine that is happening in a traditional computer that infers the error and corrects the error, or takes the decision to correct this error. And this needs to be fast, otherwise we will not be able to suppress these errors exponentially as we expect to obtain the fault-tolerant quantum computer that will be able to run these algorithms. So for that, there are a lot of research being done in doing this integration with HPC and to identify all these errors, because once we have chips and quantum computers of millions of qubits, that means we need even more millions of qubits to encode the quantum information with quantum error correction, and then we need to correct all of them. So that is a very tricky protocol that needs for this fast integration. And finally, with these hybrid quantum classical algorithms that are more at the short term, very briefly, so how they work is that we have a quantum circuit that depends on certain parameters, and we need to optimize these parameters somehow. So we obtain some solution from our circuit, some output, and this output has to be optimized in a classical subroutine outside. And this classical subroutine could be just a minimization subroutine from SciPy, so we use that as well. So this subroutine will recommend a new set of parameters for our quantum circuit, and we repeat this loop over and over until we converge towards some particular solution. So in a way, this classical computer is helping to design the optimal quantum circuit. The optimal in the sense that maybe some of the quantum gates are not perfect, so we can find some fine-tuning in the parameters in order to converge to the most prolific solution. So these algorithms are really good are really versatile to be used in different applications. We use them in chemistry, we use them in artificial intelligence, in machine learning, in optimization, etc. And more importantly, they can be run in short-term quantum computers. But how does the future look? So eventually, we will need to connect different quantum computers all together with quantum links, which is also technology that has to be developed. But even in the short term, we will need to connect them with classical links. So we cannot put as much qubits as we want in a single quantum chip. So eventually, we will need to have different quantum chips that are connected one to the other. And that means that at application level, we need to cut our quantum algorithms, our quantum circuit, into different parts and run them in parallel in these different QPUs. For that, there are techniques called circuit cutting or circuit knitting that cut this quantum circuit into smaller parts, and we can run them in different places. I think it's also a very interesting application, not only for looking at the future, because we will need that eventually, but also at the short term. Because imagine that I have a quantum computer of only 5 qubits, but then my quantum algorithm has 10 qubits, 20 qubits, 100. So I can split this quantum circuit into 5-qubit parts and run all of them in my quantum computer, or I can even simulate some part of this circuit and decide that to run in real hardware 5 qubits, and then the rest of them simulate them with supercomputers. So that's also a possibility. So I believe that this circuit cutting application is a good trial field to develop this quantum-HPC integration and see how this works and how these two different machines can be connected. We need to be very careful with this integration, because if we don't orchestrate that properly, the quantum processing unit could be a bottleneck. And let me explain why. So imagine that we have our quantum HPC algorithm that is divided into 2 parts, the quantum circuit and the classical subroutine. So both of them will follow different steps according to their hardware. And finally, we put everything together in the post-processing, and we obtain some particular solution. We can decide to repeat the cycle all over again, depending on the application. What happens is that the tempos that are managed in these two types of machines are really, really different. Of course, it will depend on the application in particular, but in general, depending on the quantum technology, the tempos could be very large. So that means that we need to wait until the quantum computer has finished in order to put together all the pieces and reconstruct the final result. So we need to orchestrate that properly, because otherwise we can spend most of our time waiting until the quantum computer is done, or maybe waiting until some of the quantum computers have finished some part of the application. So for this reason, we decided to develop a quantum-HPC workflow at the BSc, and in particular, we are extending the task-based programming model called computation, which is a tool that has been developed at the BSc from the last 10 years in order to support the quantum computing nodes that we are installing in our facilities. So the good thing is that we are using a tool that has been extensively used in the last years to orchestrate different types of applications, and now it will support the quantum computing nodes as well. And in particular, it uses sequential programming. It's also infrastructure agnostic, so we can install it in different devices, so it will not be targeted exclusively to a particular quantum computer. We can adapt it to use other types of quantum computer. And it uses standard programming languages, and in particular, Python is one of those. And Python is the programming language most used in quantum computing. So it's very convenient for us because it already works with Python. Let me show you how it looks. So for instance, for this quantum circuit cutting application, there are two ways to do these cuts, the wire and the gate cutting. Of course, I will not enter into details, but this is how it looks like, what is one of the outputs of PyComs. So what it does is, once I send the application to this task manager, it creates different tasks that will manage all the resources that are available. So it will check if the supercomputing node is available, it will check if the quantum computing node is available, and we can start parallelizing everything that we can in order to make the things as most efficient as possible. And also in order to manage all the different jobs that are created, because I need to repeat my quantum computation multiple times, so that imagine that I can control the jobs that are controlling that, and also I can control what is happening in the supercomputer. So as I was mentioning, this kind of framework will be very useful for us, because COMS is being used in different applications that have nothing to do yet in quantum computing, like biomedicine, AI, manufacturing processes, science applications. So in the end, we have now a framework to test different applications in quantum and HPC. So now that we are developing this tool, we can start exploiting it for different applications that maybe they can mix quantum computing resources and see if we find some advantage or if we find novel and new applications. So that's from the software level, but what about the real integration? So how are we connecting this quantum and HPC infrastructures? So first of all, our vision is going to the full integration. That means that both HPC and quantum computing systems are installed on site and integrated under the same infrastructure. So that means that the user will enter into this infrastructure using a batch system, as happens with traditional HPC. All of them are under the same network, and they share the same storage. So the storage will be shared between the quantum and the HPC nodes. Then we use Slurm to create all these queues, and these queues, there are the HPC ones and also the quantum ones. And we are going towards using a federated Slurm to control these different types of queues between quantum and HPC. So another thing that is important in our center is that computers are installed turnkey. That means that all the daily operation and management has to be done by BSc personnel only. So we don't want to rely on specific vendors to continue with the operation, with the daily operation once the machine is installed. And that's for two reasons. First, because we are installing a machine that technically should be operational. Otherwise, it couldn't be installed in a supercomputing center. So if it's operational, then we should be able to operate that. And secondly, it's because we need to learn how to control this technology, because if we are integrating this into our infrastructure, we need that our technicians know how all of this works, how we can turn on the quantum computer, turning off, integrating it with the rest of infrastructure, etc. So this is our job as supercomputing centers, and we need to learn with this new technology as well. Of course, this is very challenging because we are talking about a completely different technology, but it's part of our job to learn and prepare for the future of supercomputers, which will include these quantum computers as well. So for that to happen, of course, we need that the vendors develop the necessary tools to operate these machines by non-experimentalists, by HPC technicians. And that means that we need proper system monitoring, we need automatized and efficient calibration, because quantum computers need to be calibrated, and then we need a low maintenance technology. So what happens is in quantum computing, there are different types of technology platforms, and some of them are really, really good, but they require a laboratory around them. So, of course, we cannot target this type of technologies because we don't have a laboratory, we have a site. And that's why we try to identify which technologies are have a higher TRL to be installed outside of a laboratory. So let me show you, this is Mare Nostrum 5 ONA, which is our quantum computing partition. We put that name. And at the moment, it's composed by a superconducting circuit digital quantum computer that is already installed in our facility. And in the future, we will have probably next year installed a superconducting circuit analog quantum computer. Superconducting circuit because our facility is already prepared for superconducting circuit technology. And analog because it's a different way to perform quantum computation. So we believe that from a user perspective, it could be very interesting to test different ways to perform quantum computation. And for the case of the digital quantum computer, this comes from the Quantum Spain project, and it's a collaborative effort from the Spanish Supercomputing Network and 27 Spanish institutions. So basically, every institution in Spain that knows how to program a quantum computer is part of this project. And our goal was to have a public quantum computing infrastructure available for all the Spanish users through the Spanish Supercomputing Network, through competitive calls. And then for the second quantum computer, it's an effort from EuroHPC. So EuroHPC is installing quantum computers in different parts of Europe, in different hosting entities, and Spain is one of these hosting entities, and in particular, the Barcelona Supercomputing Center. And our consortium is formed by BSc, IFAE, is also a high-energy institute in Barcelona, and the Iberian Nanotechnology Laboratory from Portugal. So this is how Mare Nostrum 5 will look like once we integrate the quantum computing partition. As I mentioned before, the storage will be shared. We use the same storage as current Mare Nostrum 5. And we have a general purpose partition. We have an accelerator partition. This is a Prex-scale supercomputer. And now we will also include this Mare Nostrum ONA partition, which is the quantum partition, which has installed the digital quantum processor that we will have eventually 35 qubits at the end of the project next year. And we expect to welcome an analog quantum processor next year once the tender has finished with EuroHPC. So let me show you how this looks like, because it doesn't fit in the same room as Mare Nostrum 5, but we have a very nice place to install this quantum computer, which is the old chapel from BSc. So those of you that have been at the Barcelona Supercomputing Center will be familiar with this site. So this is where the first supercomputer in Spain was installed. This is a chapel that is located in the university campus in Barcelona. And we have here the Mare Nostrum 1, Mare Nostrum 2, Mare Nostrum 3, Mare Nostrum 4, and unfortunately, Mare Nostrum 5 didn't fit there anymore. So that's why we have a new, modern and bright building very close to this chapel, and they are both connected with a single corridor. So that means that we have this very beautiful space free, and we decided to install the quantum computers here, and we will also install other devices next to it. So now we have these two superconducting circuit quantum computers. At the moment, only one of them has a chip, which is the one from the right, the one that is open, and you can see in this picture. And in the future, we will also install here the EuroHPC, the second analog quantum computer, in the same site. So this is very convenient for us because it is perfect for visits, for visibility, because we are a public institution, so we want to explain what kind of things do we do. We want to share this with, even with high school students, with children that comes to our center to learn what kind of science is developed there. And we want to share and show as much pieces as possible, even though this piece it will not be shown all the time, because once it's cooled down to millikelvin, you cannot see the inside, but we want to be as transparent as possible. So let me finish my talk with some challenges and opportunities that I personally identify in this quantum HPC field. First of all, it's not only focusing on how can we do that, but also why we want to do that. So it's not like a magic band that I put together a quantum computer and an HPC, and I have automatically an application or accelerator. So normally we use this term of accelerator to describe the quantum computers once connected with HPC. But I personally think that it's not only accelerator in one direction, but in the other one. So HPC is accelerating quantum computers as well. And I just show you some examples of these hybrid subroutines, right? But it's not about just connecting them, because the connection is the easy part. I mean, OK, I create these federated Slurm queues, and I create these hybrid workflows. Of course, this could be tricky, but this is something that we know how to do that properly. The problem is why we want to do that. So what kind of applications require this HPC and quantum? So not only a simple laptop, but HPC, a full supercomputer close to a quantum computer. So that's why I think that quantum HPC integration must be also application-driven, because that will be the way that we make it possible in the most efficient manner. And I already mentioned some of the applications that can run this way. For instance, quantum error correction, these hybrid algorithms, and who knows what other applications, because once we have all this integration, or at least a first level of integration in our centers, I'm sure that the users that will come to us to use this infrastructure, they will find novel and new applications. And then another important caveat is that quantum technologies are diverse. So there are different types of quantum computing technologies. I just mentioned superconducting circuits because it's the one that we are installing, but there are many more. We have photonics, we have cold atoms, we have trapped ions, and each of them is completely different in a sense that it requires different maintenance, it has the different operational needs, and also the quality of the qubits or the quality of the quantum computer is really different. So the quality figures from quantum hardware, we learn about the number of qubits, but there are other figures that are really important. It's not only about the number, but also the quality of these qubits. So what are the coherence times? What are the gate fidelities of these qubits? And also what are the gate times and initialization times? Because if the gate takes a lot of time to be executed, then it doesn't matter that the coherence times are large as well, right? And what are the qubits connectivity? Because if all qubits are not connected to one another, then that means that some quantum algorithms require some extra layers of abstraction in order to fit the quantum circuit into the topology of the chip. And then there are other figures that are important and that are operational, which is the maintenance cost, what is the operational time, what is the calibration time cost, because imagine that I have to calibrate this device every day for 5 hours. That means that I cannot share the resources with a lot of users. So this is something also important for us. And my takeaway message here is that there is no unique benchmark to certify the quality of quantum computers so far. So we are all working on different types of benchmarking protocols, and at the moment, some of them are really targeting particular technologies. So of course, this is work to be developed, and this is part of our centers to develop part of this work. And also, with the introduction of HPC, that could create new figures for this benchmarking. So unfortunately, we don't have an equivalent for LIMPAC in quantum computing, but it's also our job to try to find these benchmarking protocols. So let me finish my talk with some takeaway messages. The first one, I hope that I convince you that quantum computers will not replace supercomputers. They are becoming one of the partitions, as happens with the accelerators. That the quantum algorithms have always a classical subroutine, and that's why we need traditional computation for sure. But we can go further, and we can exploit these subroutines to perform different applications much better than with the standalone quantum computer. HPC centers do not contain laboratories. We have sites, and that means that the technology that is installed in our centers has to be operational and has to be managed by non-experimentalist technicians, by HPC technicians. And that means also that sometimes it's good to collaborate with the vendors in order to find what are the most suitable tools and software to make this integration and this installation the most soft as possible. That the development of hybrid quantum HPC applications will require, for sure, a good workflow and runtime, because the execution times are very different in HPC and quantum computers, so we need a good way to schedule all the parts of the algorithm. And finally, we are a public institution. So that means that we need to adapt to user needs, and we need to guarantee the democratic use of all types of computational technology. And if our users require quantum computers, then it's our job to try to install these devices and to open it to everybody that wants to use them. But we are also a research institution. That means that we also exploit this technology, and we develop these necessary workflows, for instance, but also the applications that will use this quantum-HPC integration. So that's it. I hope that you enjoyed my talk. I'm happy to answer any questions. Thank you.
Okay, thank you, Dr. Cervera-Lierta, for a fascinating presentation. So we have a lot of time for questions and answers. So please come to the microphones in the center of the room. I see we have a few over here. Please go ahead.
Hey, thanks for the great talk. I'm Xiang Yu from University of Washington. I have a question about if you develop hardware with integration of the quantum computing and the classical computing, will this change the compiler design and operating system for that? And the second one is, do you think about using quantum computer to design the classical hardwares?
OK, let me start with the second one. So yes, that's also a possible application, using a quantum computer to design classical computers. Of course, this is a highly sophisticated optimization problem. And in quantum computing, we also tackle this kind of optimization problem. So I wouldn't say that there is a unique way to do that. Like, yes, there is this algorithm that we are using. But I'm sure that this is work in development. So I think that will be very interesting. Or designing quantum computers with quantum computers. We are also working on that. And could you say it again, the first question?
The first question is, for your new hardware, will this affect your operating system design and the compiler design for the integration of the quantum computing and the classical computing?
So could you say it again? Sorry.
Operating system design.
Operating system?
The effect on operating systems of this integration.
You mean that if they are affected by the other system somehow, or?
So the hardware, you integrate the quantum computing and the classical computing for your new hardware in Barcelona, I think.
Yeah.
And will this affect your operating system design and the compiler design for this new hardware?
OK. Not yet, I would say, because at the moment we are just installing whatever is in the market in our center. But in the future, I think, and thanks for the question, yeah, that will be very interesting to do this co-design of this quantum-HPC system. So at the moment, I would say we are talking about an experimental technology that still has to be developed much further. So I think that we are following the first step, which is installing whatever is available in our center and doing this integration. But I think that the next round will be to ask for a particular type of technology and maybe ask for a full system, including the quantum and the HPC together. And for sure, with our experience now, the next round that we upgrade our system, we will have much more knowledge about how this works, and we will start imposing certain things, because we were thinking about this quantum HPC integration with our software, right? So that's why it's really important, I think, for supercomputing centers to start working on this, because we are getting prepared for the future of these heterogenic machines.
OK, thank you.
Thank you.
Hi, I'm Silvina Caino-Lores from INRIA, France. First of all, thank you for the lovely presentation. It was very clear. We learned a lot, I'm sure. So I'm curious about what's your take on the data management related challenges at the workflow and storage levels in this coupling that you presented?
So at the moment, I cannot say many things because I didn't have the experience yet of all this management. So we are working with toy models, let's say. So we don't require a lot of storage yet. But in the future, that will be very important because each time that we measure a quantum circuit, we obtain some particular signal, so the zeros and ones, let's say, our bit string for all the qubits. So now it's easy because it's only 5 qubits, or it's only 10, or it's only 100. But once we have millions and millions, we need to save all these results and before we use the second round of iteration. So that's a huge probability distribution. And somehow we will need to cut the information somehow. So we will need to not store absolutely everything, because otherwise we will need petabytes and petabytes of information. So I think that's a very important problem to be addressed for the future quantum computers. We are not there yet because we have only a few qubit devices, but I think that the first step is to start to getting familiar with all these data storage solutions, because we will need that in the future for sure.
Thank you.
Thank you.
Okay. I don't see a question at the moment. Please come up, though, if you have one. While you're thinking, I'll ask a question. On the resource management side, so you'll have a big HPC system with millions of cores, and you might have one quantum computer. So how would you do the scheduling and resource allocation if you have millions of cores all trying to get to a single resource?
So yeah, it depends on the application, first of it, because some application may not require all these millions, of course. Maybe we only need a few of them. So that's why I encourage to be application-driven, because depending on the application, we will decide how many nodes do we need. But then, also, if I only have one quantum computer, it depends on what do you want to do with that. So do you want to run absolutely everything in your quantum computer, or do you want to split it? And that's the example that I show about the circuit cutting. So imagine that I only have 5 qubits, but then I have a lot of supercomputing power next to it. Then I can simulate very, very large quantum circuits with that. So it's a matter of choosing how many qubits I want to cut. And this choosing could be also tricky, so I might use the HPC to decide what is the optimal cuttings, and then run most of them in the HPC nodes and only a few in my quantum computer. So it will depend on the user, it will depend on the application, and our goal is to make things as easy as possible, in the sense that it will be the choose of the user to decide how many nodes they want to use eventually, or how many qubits they want to simulate, and we can try to allocate the necessary nodes to do that.
Okay. So do you have users already lined up, scientists, who say, I really need a quantum computer to do this sort of simulation? Or are you first going to build the system and then try to find users with killer applications?
It's a mixture of both. So in our experience, now the first users of quantum computers are quantum computer scientists, basically. So people that knows how to use these quantum computers. So I'm not sure if, I don't know if we can come back to the presentation, but I have some backup slides, because I think that we have some challenges, but anyway, I can just mention it. So one of the things that I think could be most interesting of integrating this quantum and HPC is that, of course, that needs that to HPC people to come and use a quantum computers, that requires a special training, of course. So I think it's a great opportunity to adapt certain courses to explain to HPC experts how quantum computers work, and the other way around, so quantum computer scientists how HPC work. And that will create the users of the future. So far, the users that are not experts in quantum computing are people that they are really interested in seeing how they can bring their tools to quantum computing. And it's great because, for instance, me as a quantum computer scientist, I have no idea about HPC until I started working on that, and I'm still not an expert at all. And it's really interesting to talk with HPC people, because, of course, you have to leverage the language, because with all different languages. But then you learn a lot about the way of thinking of HPC, and you can start seeing how this can boost our field. And we need HPC to boost quantum computers. So I would say that at the moment, the users that come to our center are people that just want to play with it. And that's also our job, to provide the necessary tools so they can explore, just exploring. And then very sophisticated users that know exactly what they want to do, so they just require the hardware to do that properly.
Okay, I see we have a question in the center here.
Is that working? Oh, you can hear me? Hi, Scott, nice to see you. Alba, so as I've been walking around the supercomputing floor, talking with users here, I mean, they're very much interested in, what can they use quantum computers for in terms of like end applications and running end applications. And a lot of gate model systems are still relatively small scale. Are you guys looking at other quantum modalities like measurement-based quantum computing and quantum annealing as well to be able to stretch into some of these application areas?
Thanks for your question. Yes, actually, that's why we target an analog quantum computer after our digital one, because we want to have the most heterogeneous infrastructure. Measurement-based could be the next step. Why not? What are our limitations is depending on the technology. Is the technology operational or it's not? That's the main thing, actually. So installing different types of quantum computing technologies, so instead of superconducting trap ions and so on, so forth, it's interesting for us, but not as interesting as having different ways of quantum paradigms, because it's programmed in a different way and the target are different applications. So of course, I would say that we are interested in the most possible heterogenic infrastructure, but it will depend on the hardware. It will depend on if there is a vendor that can do that, and if what they can do, it can be installed in a site and not in a lab.
All right. So with that, let's thank Dr. Cervera-Lierta again.
Thank you. Thanks.
Thank you. Our second speaker is Dr. J.M. Gambetta from IBM Research. Dr. Gambetta is the vice president in charge of IBM's overall quantum initiative. He was named an IBM Fellow in 2018 for his leadership in advancing superconducting quantum computing and establishing IBM's quantum strategy to bring quantum computing to the world and to make the world quantum safe. Please welcome Jay Gambetta.
Hi, everyone. Thanks for having me. This is the first time I've been at Supercompute. So I'm going to start by saying that at IBM, we're all in building what we call quantum-centric supercomputing. I'm going to go in and tell you about what it is and show you some examples and show where I think HPC and quantum is the only way to achieve this goal. So I don't need to tell HPC people, but you've been on a journey for a very long time, from CPUs to vector machines to massively parallel machines to micro and to GPUs. On quantum, we've been following a journey on making the technology exist, showing fundamental principles. Last year, in 2016, we put an IBM quantum computer on the cloud, and then we built large-scale quantum computers, achieved this thing called what I call quantum utility, and now I'm going to show you workloads for quantum-centric supercomputing. But to take a step back, why quantum? Well, it is the only technology where the math is entirely different, where it's branched. It's a new form of math, a new form of primitive, and from a complexity, we know that essentially problems that we thought were hard on a classical computer can become easy. Most famous is factoring. Other examples are simulating quantum mechanical properties. And so quantum opens this lens of looking at a new set of problems. For those that don't know what quantum is but have a grounding in classical, I like to think of quantum as just putting negative signs on essentially probabilistic vectors. So if you understand classical, you'll have a bit, you can have a probabilistic vector. If it's stochastic, you can have an exponential matrix that encodes it. But we all know that classical evolution can be written in terms of an efficient way to handle that exponential. Whereas in quantum, you get this thing we call quantum phase. People in the community call it superposition. Through superposition, we create entanglement, and there's no way that we can simulate this effect of this exponential, and it leads to us doing correlations. From an operational perspective, what we do is we execute this thing we call a quantum circuit. And a quantum circuit is just a coherent set of operations. Those in classical that know reversible computing, think of it as very similar to that. It's reversible. Most of those coherent operations, whether they're the superposition gate we call the Hadamard, C0 that generates entanglement, can basically be implemented, and we do basically a bunch of qubits. You can think of this as your memory, and then we do the gates as a function of time, and you can think of these as your operations. Of course, we can insert what we call irreversible steps that allow us not to change the complexity class of what's possible with a quantum computer, but it potentially makes things easy. This example is showing teleportation. So think of the quantum circuit as the unit. And we actually know a lot of applications of quantum computing. I go around and people always ask, what is a quantum computing going to do? You can find, you can go to the quantum zoo, you can find applications. But the truth is, I wanted to point out two regions. So if we've got the circuit size, the number of gates in that circuit, and the circuit width, if you're below 100 qubits, you can simulate it on a classical computer. And in my opinion, you're wasting your time just even experimenting with anything less than 100 qubits. If you're less than 1,000 gates, again, you can simulate it with a different type of technique. So this shaded regime I call pre-utility. Now, of course, we have these applications, whether it's for spin systems, chemistry, materials, cryptography, optimization, and they require a lot of operations. But there's this white space. And the truth is, where we are with this technology is in just crossing this boundary, just crossing what I call utility, which I'll define in a minute. And so this is exciting because this white space is where we want to explore and look at some type of applications. That being said, IBM has a roadmap. The roadmap goes out for 10 years. It includes realizing what we call in the field a fault-tolerant quantum computer in 2029 and a larger one in 2033 that is capable of doing those algorithms I showed on the previous page. The two things I want you to get when you look at this roadmap is first, that we've executed everything that we said since we started putting the roadmap out in 2020, and we're building up the stack to make programming and bringing classical and quantum computing together to create this quantum-centric supercomputing vision that I'll go in to realize that. So we have a roadmap to get those large algorithms from before, but in the near term, we actually have proofs. I love this paper. The paper was from a few years ago. What it actually showed was you can prove a separation between classical and quantum even for short circuits. It turned out this was a game. It's a typical game. It's not that relevant. But as you extend this, the field has basically found many different ways of giving you a view of what it means to be difficult for running on a quantum computer. And my view is the complexity hardness of the circuit is the only reason you want to actually look and find quantum application, and that's where we're going to find quantum advantage. Now, there's one approach to quantum advantage. I'm going to call this, there's two approaches. I'm going to jump into the first, the sampling approach. The idea here is that a quantum computer just executes some circuit and then gets some bit strings. Famously, Google demonstrated this a few years ago. From a theoretical complexity point of view, I actually find this great. This paper by Scott Aronson actually established the hardness of this problem. The actual problem with this method is, in my view, three things. One, it's very hard to actually verify that this circuit is actually hard. However, there's new ideas that have come up with peak circuits that come into this that could be potentially. The second is it's very hard to actually certify the outcome from this circuit is actually accurate. So you can't really believe its outcome. And third, and this one is saying even in the presence of noise, the samples will be corrupted, but some of those samples will lead to, that will lead to a polynomial efficient algorithm to do it. However, this polynomial has basically a scaling that goes as 2 to 1 over the gate error epsilon, so even for 10 to the negative 2 error rates, that's a 2 to the 100, which is already, doesn't make it actually useful. The approach that we took at IBM, I call it the observable approach. And so in this, for this near term, I want to start slightly different. I want to say, I'm going to give you a circuit, I'm going to give you a set of observables, I'm going to run them on a quantum computer, but I'm going to come up with algorithms and procedures that guarantee accuracy to give you error bars. We called this error mitigation because I wanted it to refer to something different than error correction, but the goal was to give you accuracy. The cons of this is the runtime is now not polynomial, it's exponential. Secondly, there also exist polynomial algorithms that could look at this. And third, the hardness of this cannot be put on the same grounding as the hardness of the sampling of random circuits. And I'll go and jump through these three to give you a feel. So first, we've been making a lot of progress experimentally demonstrating error mitigation, making bigger circuits, showing that it scales, getting to very large circuits. But to kind of jump in and give you a view, and for those that don't know quantum math, I'll give you a little bit of a high level. Essentially, you have these circuits that are represented, and they go from basically from the left all the way across to the right. They apply some unitary operation, and usually there'll be some noise lambda, and then there'll be some recovery that we want to do, like cancel the error, okay? And we'll do this iterative many times. Error correction is the only way that we know that that recovery map can be implemented to give you basically an efficient single-shot realization of this. However, the things that are required to implement error correction, I can do a whole talk on that. I'm not going to, but I'm just going to say there's 5 things that need to be done. No one has done them, no matter what you read. Error correction has still got a lot to be done to get all of them, and that's why it's going to take us to 229 to actually do it. Okay, so the other way you can actually implement this recovery map is you can say, well, can I resample it so that I can add different circuits together to effectively remove it? Another way is you can do post-selection, throw out a lot of the results and only keep the ones that you like, or you can do a combination of them. And there are also theory papers that show those come together. So all of these fields of, all these things of error mitigation, error correction, they're all based on the same idea of implementing a circuit and implementing it in a way that we cancel the effect of the noise. You can do a Hoffing's bound and get those error bars I said for error mitigation. I'm not going to go into the details other than say some quantity A, some noisy quantity AN can be bounded by a parameter that goes, we call it gamma bar to the ND, okay? And so you see that this gamma bar to the ND is exponential. So we've always known that this runtime is exponential. In fact, the runtime J is gamma bar to the ND times some rate at which I do circuits times the depth. And you can intuitively view this gamma as 1 plus a small epsilon, okay? In fact, in the theory paper that we originally did this, we pointed out that essentially you find these runtimes are like 1 plus some small parameter epsilon to L. I apologize for the notation in our field. We seem to use all over the place. L here is just N times D. So in this sort of error mitigation, this independence, this ability to run these is independent of the circuit. It gives you a way to get error bars. It gives you a weak exponential. Of course, there have been now many different other papers that have proved as well this exponential runtime, and many times it's given as an example of why it doesn't work, but they all actually get essentially the same parameter, the same formula as some error rate to the power of the number of qubits by the depth of the circuit, so the number of layers in it. So you might think then that this error mitigation is dead on arrival. Let me put a few numbers. So if I want to say 100 qubits and a depth of 100, if I take an E epsilon, an error rate of 10 to the negative 2, we find that 1 plus epsilon to the n squared is essentially 2 to the 144. Definitely outside of what we can actually possibly even envision from a runtime running in anyone's lifetime ever. But if you do the same for this polynomial that is n to the 1 on epsilon, you actually find the same. It's a ridiculously big number. But if we make a factor of 10 improvement in the error rate, this comes down to 2 to the 15. The other one goes up to 2 to the 660. If you make another factor of 10 in the error rate, it actually comes down to 2 to the 2, and the other one is 2 to the ridiculously big number. So the fact that even though there exist polynomial errors, algorithms to simulate them, the polynomials scale so badly that they make them impractical, the exponential, as we improve our error rates, actually gets them down to a runtime that actually can make them run and give you accurate results. And if I compare where our errors are on the system, we see we're right in that range. We are now crossing 10 to the negative 3 and hitting down towards 10 to the negative 4. So for the two cons of its exponential to runtime and there exists a polynomial, I can get you accurate results, one, on a quantum computer in a reasonable amount of time. So from a kind of view of trying to understand the complexity side, and I'll come back to this later. Imagine you're doing some type of configuration. I give you some configurations, and you're searching over this configuration using a decision tree. You'll connect all these different parts, and you may use a lot more. What I've plotted here is down the number of useful configurations relative to the total number, until you get to an error bar of estimating some quantity, some observable, and I've plotted the error. You may use a lot before it actually comes down. What we can actually show with a quantum circuit is it can project you into those configurations. We can numerically do it, and we can show that it actually best uses these configurations and allows you to give that sort of view. So this sort of notion of a quantum circuit projecting, helping you find, is where we see this sort of areas to look for advantage. We've also looked at circuits in optimization, where we can actually come up, this is a famous paper by Ed Fari, look at optimization, where you can come up with circuits that will be potentially useful for these problems. My team at IBM has looked at what we call hardware-efficient circuits that can be used in chemistry, and what we call correlation circuits, which can be used in machine learning. So there's all these circuits that are sort of filling up this belief that they're hard. But last year, a big result happened from our perspective. We were able, the first time, to be able to run on a quantum computer an accurate quantum circuit on 127 qubits and approximately 3,000 gates, which is well beyond brute force classical computation. It cannot be simulated exactly using a classical computer. I'm going to give you a little trivial example. So here, if it comes up, sorry, animations are not working. I have a bunch of 10 different black boxes here. Each one of these is going to represent a different experiment. And I'm going to plot a parameter on the axis I call z, and a parameter on the x-axis I call theta. And I'm going to show basically each one of these gives a different value, okay? All of them are different. None of them are the same. What is truly, and in fact, if I take a sort of 80% confidence on them, they're about 20% different. What is truly amazing is one of these is actually a quantum computer. And this is what we meant by utility. It is able to run a computation where the leading tensor methods all give different results. I cannot tell you which one of these is more accurate than the other, okay? We're now at a point with our quantum computers at this scale that we can view them as a scientific tool. And even more, the methods, the new methods they're inventing in tensor methods are getting convergence. They're doing convergence, reliability, based on converging to an experiment. So quantum is at the point that the new improvements in these tensor methods are using the convergence criteria to be that it realized what was in a quantum computer. And so what we mean by utility is we're at a point where we cross and we have an exponential scaling. It's a weak exponential. It's not, we have to get error mitigation to error correction working. But we're at a point where we can now run circuits, and I can give you accurate results that are beyond what you can actually simulate with your brute force classical computing. So 2 years ago, we set the goal that we wanted to actually get to a point where we could run circuits of 100 qubits, depths of 100, whether you wanted to go by 100 or total number of gates is around 5,000, and basically get accurate results on a quantum computer. And I'm happy to report that this is possible. So here's a circuit of about 5,000 gates, and it's essentially running a very simplified circuit. It does some type of trotterization and then mirror trotterization, so I know the outcome. But 60% of the 1 qubit observables on this circuit I can get with an accuracy of 10%, and this is what we set on that challenge of getting to 5K. Other methods, so here's a method by one of our partners, sorry, I looked at the wrong slide. And then even more improved results are emerging, where this is going up to 97, these are still research. The blue you can actually run using our systems on the cloud today. The pink method is new research that we'll bring out soon. Our partners are also developing what we call, another form of error mitigation. And this error mitigation is called tensor method error mitigation. And essentially you have the noisy circuit, And now what you do is you run a tensor simulation of something that is almost equal to the identity. So something that is easy to contract because you go from the middle out to allow you to get an accurate result. And in fact, it has a better sampling than the other methods, but it does require actually using GPUs or HPC to actually do that simulation. And doing this, we can even look at different types of circuits and again get around the 5000K. And we can go to a point where those circuits have an analytical solution. We can verify that they work. And then we can go beyond where we can't do a brute force. And we find that some of the tensor methods agree with what we get on a quantum computer and others don't. So confirming that we're in this new regime. So now I want to switch slightly to a little bit different and kind of get what I mean by another form of quantum error correction that is definitely suited for what, let's say, the quantum-centric supercomputing architecture. In this, I want to look at a chemistry problem, say Fe4S4. If you are going to do a fault-tolerant implementation of this, you'll have to do what is known as phase estimation through the estimation of the phase, get the accurate results. But it's going to require error correction in about 5 million qubits. And if you do some estimates, it'll take about 13 days to run. If you were going to do the trivial way of essentially error mitigating every term in the Hamiltonian, so there's 6.7 million operators in this Hamiltonian, it would actually take 3 million years for us to run the error mitigation things. And so again, that's another example of something that I would say is not practical. However, I'm going to show you a method that projects a quantum computer into a lower subspace and then allows us to feed it into a large classical computer and get this runtime down to about 2 hours. So we take a circuit. This circuit has some chemistry properties that I don't have time to go in, but it sort of represents basically hitting it with different types of coupled cluster approximations and allows me to look at those, say, fermionic problems like the chemistry that I put up on the, like iron sulfur. Then what we do is we essentially sample this based on our quantum computer. So we run it on the Heron processor, and then we put all of this data into Fugaku, which is a supercomputer in Japan, and then we do what we call a configuration recovery. We look at a set of observables, we take that configuration, we diagonalize it, so do an advanced diagonalization method on the supercomputer, iterate, see what the occupation numbers come, and iterate that many, many times. And what is really cool is following this method, we are able to reconstruct chemistry molecule things, so like N2, which I would argue most people thought would not be possible. The quantum in the brownie color works better than the approximate methods like Hartree-Fock and the classical methods, say the blue and the yellow, and sort of represents the distillation more accurately. It also, as we scale up to iron 2, sulfur 2, it gets to the point that we're getting to the same accuracy as you would get with leading chemistry methods like DMRG. So those that are chemists in the field know these methods. I am not saying we're beating it. I'm saying at this point, we're getting to the point that we get close. If we go a little bit further into a bigger molecule, we get better than random sampling, but we're still, the noise in the system is stopping it to work. And so this sort of points out as we make improvements in the noise, this was run with about 3,000 gates, things will get better. In fact, this same method, because of the versatility it can, and the way that we are developing in a way where all of the software is open source, can easily be added to different types of problems. And our partners at Cleveland Clinic, Lockheed Martin have looked at different types of simulations, whether it's from water diameter to molecules that are for propulsion and other types of things. Okay? So the method is definitely stable, it works, and it's starting to go through different types of examples. And then as we've made improvements in the device fidelity, as I told you before, we've just recently been able to get this method to 5,000 gates. And so my view is we're now at the point that we have a quantum computer that can give you accurate results at 5,000, which is beyond brute force, and then there's an interesting question of how we start to use it. And that's where we lead into what I call quantum-centric supercomputing. And to me, it's not just a larger quantum computer. It's actually what I think of is the next generation of QPUs, GPUs, and CPUs all working together. And from a workload management, honestly, it's exactly the same. You have some type of graph that represents the problem. You have, now instead of having all of them be classical nodes, you have one node that represents a quantum that executes some type of primitive. And so you can fit it within the standard workload management systems you all know. In fact, you can go even further and say some of the jobs will always use the quantum computers, some of the jobs will use hybrid. I'll need to mix it through these type of hybrid where there's single jobs as well, and I may even want to do a direct access with a quantum computer co-located or through a cloud. And so that leads to what we're developing, essentially quantum cloud bursting, where you can send many jobs directly to the quantum computers, as well as direct access type where the same API, the same primitives that are run are used in both places. So we've started to prototype this as an example with RPI, who has Amos, which is a large classical supercomputer, and also one of our quantum computers. They're actually stored close, and basically it's the perfect test bed. So we can start to do Slurm-like iterations, but because we have a bunch of quantum users that are very used to using the Python code, we want that to look like it's just how they would just work any day. So in this simulation here at the start, it showed standard way of setting up a Python job, and then it showed the Slurm integration as it went forward. So from the quantum users, it doesn't look any different. From the HPC users, it can just fit directly into the same way you're doing it. So this prototype is already working. We can run submission of jobs. You can have the mapping problem, the optimized Partition, the pre-processing all running on classical nodes. You can have the execution of the quantum primitives, calling the VPN, allowing you to execute this sort of seamlessly environment. And so the take-home I want to say is we don't actually have to invent anything. We just have to put these together, and we can actually start doing these workloads now. We are also working with our partners at Recon and installing a quantum computer right next to Fugaku, so we can even explore even faster connections between the two systems and look at extensions to the algorithm I talked about earlier. We're also partnering with Pascal because this architecture is fitting within the same way HPC is done. You can put any type of quantum computer there. You can create heterogeneous essentially heterogeneous QPUs mixed with classical and have this total architecture worked out. So my prediction is quantum advantage, where we can do something cheaper, faster, or more efficient than classical. And I know I showed you that I could run quantum circuits better than classical, but we all know classical methods are very good at actually solving problems without running quantum circuits. Quantum advantage means I can actually do it cheaper or faster or more efficient than any classical method. But I do believe this is only going to be possible if the HPC community and the quantum community come and start working together. And so I laid out a few things here. So before 3K, or less than 100 qubits, don't waste your time. Just do not waste your time. It can be simulated. It's cheaper to use a simulator. It's not interesting. In this error mitigation regime, where I can give you accurate results, you can start to look at approximate methods. And then we see the future as this continuous path to error correction and allowing us to realize large-scale error correction. I'll make a side note. I disagree with everyone that HPC is needed for error correction. Error correction is a very simple algorithm. The overhead and complexities of error correction are in building the size of the chips and getting reliability. So from a HPC perspective, I see it integrating in different ways. So first, I don't see any value in simulating wave functions. If you are going to spend a lot of money to create a cluster to simulate a wave function, it is not going to teach you anything about quantum computing. However, I do see a lot of value in the future being tensors plus circuits working together to allow us to do a lot more. So we want to create this simplified code that brings this future of tensors and circuits together. And one way you can imagine this is if you were going to use tensor methods, rather than simulating the quantum experiments we do, how do we as a community start to identify which ones of those tensors and which ones of those circuits are actually the hard ones for the tensor methods to do, so that we can use those error mitigation techniques that work for any type of circuit and actually start to build collections of circuits and observable pairs that can be like the toolbox for exploring how to use quantum advantage. And I do think quantum advantage is going to be the union of these circuits that I can run faster than I can simulate on a classical computer, as well as those mapping collections between circuits and observables that I've determined are the right candidates to actually not use tensor methods for. Error mitigation. Because we are doing tensor methods on top, or large-scale diagonalization, or we even have lots of data handling, or we even have more robust, improving error mitigation techniques with HPC, making them more efficient, making them run faster, making them actually give us the same quality result using less calls to the quantum computer. These are all open questions of how do we actually extend, how do we bring numerical methods to quantum computing. Kind of talked about before, I do think the community in quantum, it is a myth that a single quantum circuit is going to be how we run a quantum algorithm. I do believe every quantum circuit needs to be more than 100 qubits, more than 5,000 gates, as I said. But the future is going to be running clusters of quantum circuits that you glue together with various different techniques, such as circuit cutting, one that we call matrix product. I forget the last letter, but essentially you use a tensor method to infer how you add those methods together to create a larger, more accurate quantum computer. And so when I go and finish on our roadmap, we have a roadmap, as I said, that will take us from today. We're going to make larger and larger quantum circuits. So this is what we have in 5K. We've achieved 5K. Going to 2026, I want to get to 7.5, 10K, 15K. Error correction will allow me to go up to 100 million. So you can think of this as how large a quantum circuit is run. But from the HPC perspective, as we go forward, how we do the scalable circuit knitting, how we do intelligent, how we do resource management, how we do circuit knitting in more of a product lens, and how do we create this collection of circuits and observables that we should be using as the primitives to define the algorithms is what we're going to do over the next couple of years. And so on that, I hope I've convinced you that quantum is at a point now that you cannot use a brute force classical computer to simulate it. I can give you accuracy and reliability, and this is what we call utility. To get to quantum advantage, we have to mix that utility with smart ideas and tensor methods, algorithm development to get us to the final goal. And on that, I want to thank you.
All right, you know the drill. Come to the microphones and ask some questions. Please.
Jess Williams, I'm a researcher in tensor network methods for circuit knitting. I'm curious, as we move past this regime where we're able to simulate even approximately the quantum computers, what types of new methods will we need in tensors or otherwise to perform validation, benchmarking, and design of these systems?
So, most of the time that you can do the validation, you exist in either efficient analytical solutions or efficient polynomial algorithms that allow you to do it, and then you move beyond. Rather than going to small qubits and scaling up, you go to points where I can predict it. In fact, we are releasing a tool that we call NEAT that shows you how you can take your circuit, you can put it into a regime where there exists an efficient polynomial algorithm, allow you to verify it, and then allow you to go away. This is exactly the same as what people do in numerics, forgetting quantum, like just get quantum out of the word. You do numerical methods where you can validate the numerical method where you know you've got analytical solutions, and then provided I can give you error bars, or I can give you error propagation, whether it's infinite differences or those type of things, you can trust how it goes. And so my view is with error mitigation, because I can give you error bars and I can put things on there, you can trust that outcome to go beyond those type of methods. I actually think a better use of tensors is to think of tensors and circuits as equal partners and ask, how do we actually join them together? Circuit cutting is one example, but I think tensor contractions and tensor expansions, imagine that even some of the nodes turn out to be quantum circuits. And as we go forward, rather than using tensor methods to claim you can simulate quantum, switch it to tensor methods on top of circuits to expand what they, like, I fundamentally believe the math of the future is tensors and circuits. And we need to think of them as primitives, and we need to work out scientific methods that use these primitives and add them together in different ways. And I think there's heaps of ideas, like you mentioned, circuit cutting. I think the validation, there are better methods to validation.
Thank you.
Okay, let's go to the center.
Hi, Tom Marseille with Washington and Lee University. We've heard a lot this afternoon about how we're looking at hybrid computing with quantum and high-performance computing. IBM has been a leader in both quantum computing, but also has a very long history in supercomputing. And right now, we're hearing a lot about how we're just going to create quantum nodes, and we're going to just add this on to existing supercomputers. And I'm wondering if IBM has considered actually merging their divisions of supercomputing and quantum computing and developing a system from the ground up so that all of that integration is built in and being considered and engineered together.
We are very connected between the different parts of IBM. We share that the future of computing is these different things, like I said, tensors plus transactions, like summing numbers, plus circuits. If you want, it's bits, neurons, and qubits as a simple way. Just that what we are envisioning with the quantum-centric, yes, I showed you realizations that we just were integrating it with standard HPC. As we explore different types of tensors and tensor accelerators, I am 100% sure the future will be tensor accelerators mixed with circuit accelerators to get to that vision. I share that vision, and that is the goalpost. But we put it all under this umbrella of quantum-centric supercomputing, but there's a long path to do it. And I think what is cool now is quantum should now be considered part of that equation. With the utility type experiment and giving you accuracy and doing it at this type of scale, it now has almost like graduated to be at that. And so that was only last year. Our goal over the next, well, probably as long as I stay at IBM, is to bring all these together and realize a quantum-centric supercomputer that brings forward the math of the future. Well, I shouldn't say math, the realization of math that we've always known. Like quantum math has been known since Schrodinger, Einstein, and all that. But the math that can now be realized at scale, and we've got to work out how we put algorithms to these things. And I think that's the exciting part. And what I wanted to get across in my talk is we're at the point where we can, like, maybe I'm too much of a physicist, but I can put error bars. I can give you numerical confidence. And so now we can start to build that. And I know I'm not directly answering your question because I also believe some of that, how it comes together, even though we show it's easy to integrate with the Slurm or the tools, you can just do it, has to be driven by the algorithms that we discover that use these two types of math.
Thank you.
Hi, my name is Tanya. I have a PhD in physics. You emphasized over and over that anything less than 100 qubits should be classically simulable. I have a paper right here on a 56-qubit machine from Quantinuum. I'm going to read you a sentence from the abstract.
Look, it's an exponential. So I think the world record is 45 qubits. I'm making the point that 100 puts me above any innovation that happens in the classical world. It is extremely, extremely unlikely that anyone is going to get to 100. Maybe they'll get, the record now is 45, maybe they'll get to 54, maybe they'll get to 60, but that exponential just kills it, that you can think of 100 as a mark, that you're just safe, that you're setting enough. I think that is, where exactly that number is, I honestly don't really care too much. Whether it's 45 or 54, it's an exponential.
I'm not sure what you mean it's an exponential. I think that they've showed that at 56 qubits, they're no longer classically simulable, which contradicts what you said. Can you help me understand?
So 45 qubits is the exact, I think that is the record that people have done using a method called the Schrödinger method of simulating the wave function exactly. I don't know what the record is using the Feynman method, but that is actually the dimension. So if you really want to go from an exact brute force method, you draw a 2D plot. You have 45 qubits and essentially very, very long depth. So let's put that point. You have many, many qubits.
Are you talking about simulability?
Pardon?
Are you talking about classical simulability?
Yes, that's
okay.
what they're saying is. And if you want to draw the line at 56, I'm okay. 100, it's not. 100 with a depth of 3,000, no amount of energy using classical will be able to simulate that. Unless it's an approximate 10th.
But I think it's clear that at 56, it's no longer classically simulable.
They need to give you the depth. And if you do a Feynman method, I am not as comfortable saying 56 will not be done from my perspective. If they want to say it, let them. I don't care. I have set my boundary at 100 and 3,000. If you want a smaller boundary, like I said, the record is 45 for very long depths. I do not remember what the record is for the Feynman method. Don't remember off the top of my head. But I can tell you, you can do 10,000 qubits as a short depth. So you got this contour. And 100 by 3,000 is so far into that contour of not being able to be directly simulatable that you don't even bother trying.
Understood, but I don't think you're wasting your time at less than 100 qubits, which is something you did say. Thank you.
Have fun.
Hi, Eddie Zhang from Rutgers University. So I have a question that's related to AI. Do you think if AI can scale up the kind of applications that can take advantage of noisy quantum computers we have today? You mentioned the application that can predict accurately using 127 qubits and 2,880 gates in your slides. So do you think we can go beyond that for this NISQ-era devices? And if AI can help us achieve that goal? And if so, how and how that, which aspects?
Already I showed you 5,000, so we're already beyond it. We have online a AI-powered transpiler service that can help you compile your circuits much more. I am very much a fan of AI helping quantum to simplify how you set up your quantum circuits, or how you determine better ways of sort of breaking up the problem. How all these mix together is related to my point of this future being tensors and circuits.
Right. So, so we are at the HPC conference. So, if you think AI for quantum is useful, do you think it would need a HPC or supercomputers to achieve that goal?
I think you will need supercomputers for extending the methods of handling the errors and how you break up the problems. I think supercomputers for the compilation is definitely valid. Exactly the scale of that is part of the work. We're seeing some of these tensor methods allow us to do these more advanced circuit knitting that with this MPF. You could think of this as a great use case for HPC as well.
Okay, I see. Thank you.
Okay. I'll ask a question while everybody's thinking of their next burning question. So you had mentioned HPC for compilation. As the quantum circuits get, or the quantum systems get larger and larger, is there a point at which we won't have a supercomputer big enough to compile for a quantum computer?
Most of the compilation is going to be heuristics, and I imagine doing similar things that we do in the classical world with peephole and things like this. So you give more resources, you throw at it, make it better, but you're probably going to do just as good with a lot of these heuristic compilation methods, exactly the same as what exists in the classical world.
But do you think that maybe there would be a quality threshold, that as the quantum systems get larger, you need the HPC system to compile for it. At some point, you have to use the heuristics, like you just said. But then do the heuristics get worse and worse as the system gets larger and larger?
I think the scaling is going to be in your favor, because even if you could do a little bit worse, the exponential scaling on what quantum does will overweigh that. But it's a great question. It's an open question. I don't know the exact answer, but I don't think compiling future quantum systems, quantum computers, is going to be limited by our smartness and our classical resources. I think there's a lot of intelligent people and methods that we have to put together to make the compiling problem happen.
Okay. We have a question over here.
Yeah, Sergey Glazer, University of Alabama. Thank you very much for this amazing and visionary talk. Maybe expanding on the last question, I know you mentioned AI for control and things like that. What about quantum machine learning and algorithms that directly take advantage of the circuits and design them for the circuits and to take the best advantage of the QC?
Using AI to design better circuits?
No, I'm talking about directly, like algorithms, machine learning algorithms that are directly in the language of circuits. So like quantum transformers, quantum graph nodes, things like this. Quantum machine learning, like directly.
So I showed a paper by my personal algorithms that I'm interested in doing, quantum algorithms for AI. I showed a paper where we look at data that from a classical lens, you would say it's random. And there exist quantum algorithms that could tell you that that data was not random. And we've started to explore that. It's hard to really formalize that, but we call this quantum kernels and quantum machine learning. I think this is a great, exciting research direction on how we can get quantum algorithms for AI. I don't think it's going to be helping in any way big data. I think it's going to be helping when the data has some type of correlation that is, from a classical lens, you would say it's a random number.
Starting to see also advantage in that space, but again, in a very niche scenario, small models, small data, that kind of scenario.
Yeah, I think quantum machine learning is great.
Okay, I have to apologize that we are out of time. So let's thank Dr. Jay Gambetta for this really exciting talk. Thank you.